everybody, I wanted to do a very quick example problem that shows you how you could take a pretty complicated situation, in this case, oh I'm all smudgy, in this case a problem that involves a mass in contact with a spring. The spring is compressed, the mass is released, it travels for a little bit of distance, then it hits a rough patch and it skids to a stop. And your task is to figure out something about this problem. Now we could solve this problem using Newton's laws and kinematics, but that would be pretty complicated. We have this variable spring force, we'd have to determine some kind of acceleration, we'd have to use kinematics to figure out velocities at different points, we'd have to figure out how, what's happening along the rough patch over here, and we'd have to eventually use kinematics again. So we have quite a bit, there would be quite a bit of physics involved in solving this using methods that are not energy. If we look at energy though, what it allows us to do is look at an initial point in the problem, a final point in the problem, identify the energies at those points, identify anywhere that work or energy might sneak in or out of the system through work, and once we've done that, we can solve it with one master equation. So for problems like this, energy often provides a much more elegant way to approach it. Now this is a weird problem in general because let's take a look at what's going on here. We have a block of mass 2.5 kilograms is initially at position x equals 0, and that part isn't terribly important, and it's in contact with an uncompressed spring. So let's picture an uncompressed spring here, just resting. Now what I do is I push, to start the problem, I push the block back to point A, so I compress the block a distance d. We can ignore the negative sign here. I compress the block a distance d, and now I'm ready to go. So this is where the problem starts. So I have a block against a compressed spring, I release it from rest, it's going to decompress, come back to that point, and then the block is going to leave the spring behind. It's not attached, it's going to travel to point B, and it's going to travel a total distance of 3d before it actually comes to rest. And you're told the coefficient of friction on this rough patch. And your task is to determine what d is. So this is a good problem because it's not even asking for an energy specifically. It's asking for a distance. And so, like, as you get more seasoned with this, you'll say, well, I clearly want to use energy to solve this problem because it's going to be too complicated any other way. So let's just see if we can make sense of this. I'm starting at point A with a compressed spring. I'm winding up at point B. I've stopped and I've traveled along a friction-y little path there. And let's start with our most general form of the energy transformation equation. The energy forms that you have initially, which we're calling point A, gravity, spring, and kinetic, plus any work done, and that work can be positive work through a push, or it could be negative work through a drag force like friction. And then in the end, that's the energy you wind up with, the total mechanical energy. What you have plus what you gain or lose is what you end up with. And the first thing I like to do, even if I know there's no height change, for example, in this problem, I like to write out the most general form, because until you get really used to this, it can sometimes help you catch things that you miss if you do it too quickly. So first of all, we can notice there is no height change in this problem, so we can call the height of that table 0 and just ignore gravitational energy for this problem. The next thing we want to do is look at point A and say, what kinds of energy does it have? Well, there's a spring, and the spring is compressed, so it definitely has spring energy, so we have to leave the elastic energy in there. Now we say, is it moving? The answer is no, nothing's moving at that point, so I can also cross out Ka. Now let's come over to the end, look at point B, and ask the same set of questions. Is there a spring in the problem? Yes. Is the spring compressed at this point? No, there's no. Remember, when the spring decompressed, it left itself, the block left it behind, and now it's just kind of sitting there relaxed at point 0, and the block has moved on. So even though there's a spring, it's not stretched or compressed, so there's no more elastic energy once the block reaches point B. And interestingly enough, it's also come to rest, so there's no kinetic energy at point B. And this might be a little scary just to have like the whole side be 0. Totally okay, because remember, we have work. So now let's ask ourselves the last question. Are there external forces on the system, and is work being done? And the answer is yes, there is. Over this distance, there's work done by friction. And so we could say yes, this is work done by friction, and we'll be able to calculate that. So now we pretty much solved the problem, right? We just have to put in this, set it equal to 0, and solve. So let's go ahead and do that. So use spring initially. Well, we know the K. That's going to be 1/2 times K, which is 100 newtons per meter, times D squared. And we don't know what D is, but that's all right. We can leave it there. Now we have the work done by friction. And we know that friction acts opposite the displacement, right? The blocks traveling forward, friction x backwards, we know that's going to be negative work. The angle between those two, the displacement and the force is 180 degrees. So that's going to be a negative work, negative kinetic friction force, which we will have to calculate, times the distance over which it acts. But what is the distance over which it acts? Well, the friction acts from point 0 to point 3D, so the total distance is 3D. And even though we don't know it, we can just put it in, and then we set that equal to 0. And so let's calculate the frictional force over here on the side right now. So we know Fk, it's flat ground, is mu k Fn, and we know that Fn is equal to the weight because it's on flat ground and it's in vertical equilibrium. And so our frictional force should be 0.17 times the weight, which is 2.5 kilograms, times 9.8 meters per second squared. And let's calculate that really, really quick. I'm going to get out my calculator. 0.17 times 9.8 times 2.5 is, and you can't read it, that's okay, is 4.165 newtons. Great. Okay, so there's our frictional force. Now let's come back over here to our equation. So 1/2 times 100, that's 50 newtons per meter times d squared, plus, now let's put in our negative frictional force, which is 4.165 times 3d, and you could at this point change that to a minus. I'm just being super formal here. Okay, so we got to multiply 4.165 times 3. I get 12.495. So 50 d squared minus 12.495 equals 0. And you might say, oh no, I have a quadratic equation, but I don't, right? Because I have 0 on this side, so that's nice and convenient. 50d squared equals 12.495d. One of the d's will cancel as long as it's not 0, which it's not. And I get that d equals 12.495 divided by 50, which is about 0.25 meters. So that worked out rather nicely. That's it. So look at how we really only had one major equation. We had to use this friction in here, but we had one major equation. We really used force times distance for work. Remember the negative sign for the friction, because that's going to do negative work on the system, because work is F d cos theta, and if you put in the frictional force and the distance, cosine of 180 degrees is -1. So that's another way to think about that. And then you do your thing out and you get that answer. All right, I hope that was helpful. Bye.